I start. So I start with k smaller equal to 3, and immediately for k equals 1, and first situation is distribution, and there is a dimension of M equal to 3. So a distribution, let us say in R3. Two-dimensional distribution in R3. Then in R3, what is the generic situation for a generic distribution? It is contact out of a surface that I call M, because it is a Martinez surface, and except that there are several isolated points on the Martinez surface where the distribution delta is tangent to. So generically, this Martinez surface is a smooth surface, actually, generically. And there are isolated points where the distribution is tangent to this Martinez surface, and otherwise at other points the distribution is transversal to the Martinez surface. Yes. Then in particular, the intersection of the distribution with the Martinez surface defines a vector field, and the this vector field has equilibria that are these special isolated points, and the integral curves of this vector field, they are the abnormal trajectories. In that case, the abnormal trajectories are exactly these ones, but I don't care. So this is generic situation. These points are in fact of two types. There are two possible types. The vector field can be either hyperbolic or elliptic. Then there are two types, but I don't care. And I don't care at all about abnormals, but just to say that intersection of distribution with Martinez surface gives you just the abnormal curves. Now, what is the situation for a generic curve gamma in this setting? So this curve gamma generically it will cross transversally the Martinez surface, and maybe at several points, by the way. But you can assume that generically it does not, it is not generic that it crosses at the isolated special points. This is important for future. And in fact, along this generic curve gamma, almost everywhere the distribution is transversal to gamma, except maybe at some isolated points on gamma, where the distribution, where gamma is tangent to the distribution. This is almost admissible curve around this point. If you move slightly the curve gamma and the distribution, such a situation is perfectly stable, you see. Then this is the general situation. So for a generic couple of Sub-Riemannian metric and of a curve in R3. Okay, so let me first forget about these points. forget about these two kinds of points and consider a piece, consider a gamma 0, 1 to R3 such that everywhere it is contact. Contact everywhere. Delta is contact in a neighborhood of gamma. Okay. Then I consider normal coordinates. I consider the tube C epsilon along around gamma, and in fact this delta being transversal to gamma, if epsilon is sufficiently small, it will still be transversal to C epsilon. You know? Then since delta, for epsilon small, delta is transversal to C epsilon. Then in fact, delta defines a vector field on C epsilon. Delta defines a vector field on C epsilon. And this is one of the trajectories of this vector field. And what I can prove, what I shall prove, is the following. In that case, I just take the results and just give elements for the proof in this simple case. What is the asymptotic optimal synthesis in that case? It is very simple. You start from gamma 0, you want to go to gamma 1, okay? Then you just take a horizontal geodesic. We know that we have horizontal geodesics that go to and it is just to reach the cylinder, it is of length epsilon. Okay? And after you follow, so you reach a certain, you reach the cylinder on a certain curve, you follow this curve up to a point which is at the same height as gamma 1 here, and you reach gamma 1 with a horizontal geodesic that costs epsilon. And as I shall prove, this cost, exactly the cost of this is the following. Okay, I give it after. I just describe how you get the asymptotic optimal synthesis. You get it like that. Now, okay, maybe I have to state this. So this is the asymptotic optimal synthesis, and what is the value of the metric complexity? You get it like that. You consider any one form omega that annihilates delta, and omega evaluated over gamma dot is 1. Along gamma, omega is 1. So there is not a single such one form omega. If you have one omega 1, you multiply omega 1 by a certain function f. If this function f is 1 on gamma, it works also. It gives us the same. Okay? And now you consider d omega. You consider d omega, then this d omega with the with the metric, it is what is it? It is just this d omega. What is it? It is just a two-dimensional skew-symmetric matrix. It is a skew-symmetric matrix. It is a bracket. In fact, okay, it is a skew-symmetric matrix. Then it can be written alpha here, depending on W, because I do this along alpha minus alpha. It is skew-symmetric matrix. And the metric complexity as a function of epsilon. Sorry, I have to repeat. I said that the metric complexity, when I defined the metric complexity of a curve, gamma, I made a mistake. I said that it was the minimum of the length of curves, gamma, epsilon, that connect by remaining in the tube. In fact, usually people divide by 1 over epsilon, this guy. Just a normalization to count the number of times epsilon is necessary. Okay. Then usually you do not take the length, but you take 1 over epsilon. And metric complexity is then 1 over epsilon square, sum over gamma of this dw over alpha w. If you compute in the normal form, that I presented half an hour ago, there was this function gamma, and alpha w is nothing but gamma 0 w. Okay. This is when you are on a contact piece of the curve gamma. Okay. Now, what happens if you... So this is the metric complexity, and this is the asymptotic optimal synthesis in that case. And now, what happens if you cross Martinez surface? Then if you cross Martinez surface, generically you cross it for a finite number of points, 2 here, and the metric complexity becomes the following. It is, sorry, here it is 2, but no matter. It is 4 over epsilon square minus 4 logarithm epsilon over the sum over Martinez points, of absolute value d alpha wi, d alpha dw at wi. That's it. You have this alpha. It is smooth function. You take its derivative with respect to w. You evaluate at the Martinez point, and you get and so this logarithm appears here. Wow. You cannot read?
I can see, sorry. That's okay.
And the situation now is like that. In fact, if we examine the things more precisely, what I shall do in a minute, you see that almost all the lengths, you spend all the time to cross the Martinez surface. This is the surface. So now I describe the asymptotic optimal system. One remark before. In fact, at such points, tangency points of the curve gamma to the distribution, this alpha W tends to infinity, this guy. This quantity is still perfectly well defined, and the formula remains true. Then, as was expected, the points where the curve is almost admissible do not pose any problem. Just this formula continues to work. It is very easy to find asymptotic optimal synthesis. For a while, you will follow admissible trajectory in the distribution. And outside, you have this strategy. Okay, let me just show what you should do. What is the asymptotic optimal synthesis in a neighborhood of a Martinez point? What is the situation in a neighborhood of a Martinez point? Then in a neighborhood of a Martinez point, you have gamma, you have this, again, the cylinder, C epsilon, you have our vector field. It turns out that, and here is the Martinez point, and horizontal coordinate, I am still in normal coordinate, and it turned out that I choose some orientation on the vector field. It is not important. It turned out that at this Martinez point, you have a limit cycle. Here, this vector field has a limit cycle, and then it must be like that. And here, so it must, sorry, it must be like that. Oh no, of course. Okay. And in normal coordinates, due to the fact that generically you do not pass through these special isolated points, this limit cycle is not contained in a horizontal plane. Okay? If you are at these tangency points, things become different. You may be contained, maybe horizontal. Then what is a possible asymptotic optimal synthesis is the following. You choose another epsilon prime, but very small in front of epsilon. And for this epsilon, so you follow the flow of the, so again, you start here, you do this. But this costs epsilon in front of epsilon square, of 1 over epsilon square is neglectable up to equivalence. I remind you that I am interested with the metric complexity up to equivalence. I am only looking for the leading term. Okay? So I would be better to write equivalent here in the formula. It is a metric complexity is a function divided by this one tends to 1 when epsilon goes to 0. Okay? And so you follow this flow till you reach this region, and when you reach this region, you do like that. You follow the vector field till the moment you are at maximum 8. After 8 becomes to decrease. Then when you do that, you cross the cylinder geometrically with a horizontal geodesic of length 2 epsilon. And you continue like that. You cross till you reach the maximum. You do this for around the Martinet point for a certain 8 epsilon prime, which is small in front of epsilon. And once you do this, once you are here, you continue, you take again your vector field and you follow it. This is the asymptotic optimal strategy. Now, before computing and going to more complicated situation, I want to give the reason for this logarithm epsilon. Because, yes?
Please. Oh, I don't understand why this limiting cycle exists.
Why this limiting cycle exists? Well, you have to compute it, but the reason is that this gamma of 0W is non-zero in contact case, but becomes 0 at Martinet point. By the way, you can see that the formula, contrarily to these points, well, the metric complexity, which is equivalent to 1 over epsilon square, the sum of dW over so gamma 0W, it is this guy. You see that now this formula is divergent, contrarily to these points where gamma 0W tends to infinity, it is convergent, but here it is divergent. Metric complexity becomes in fact this. So why this limit cycle? Because this gamma 0W becomes 0. You just take the normal form and compute, and you see it. Because it is Martinet point. So it is a more or less universal reason. It is a more or less universal reason, this logarithm that appear. I shall explain. In fact, in many situations later, you will get at non-singular points, a singular point in this case is a Martinet point. But imagine in the case of a distribution with an anomalomy degree larger than 1. The formula for the metric complexity will be like that. It will be 1 over epsilon p plus 1, where p is a anomalomy degree. The integral over the curve gamma of dW over a certain function of dt over a certain function k of t. And it will be always the same. In other situations in the future, when you cross a singularity, then I explain it now. The reason for this minus epsilon square log. You have this at regular points. We are in the situation where we have a metric complexity which is like that. It is in particular the case of Martinet point, of a contact point in dimension 3. Okay, this formula diverges, but when you cross a surface, so through a singular point, you will get the metric complexity will just be minus logarithm epsilon over epsilon p plus 1 times 1 over absolute value of k prime of 0. Let us say that the Martinet point is at time 0. Okay? You get this form. You see, in general, you get this behavior and this formula. The reason is very simple for that. The reason is that, in fact, the reason, I do not give the details, but only the reason. The reason for this is that when you try to evaluate sum from 0 to a certain epsilon prime, say, so I will do it from okay, sum from epsilon prime to 1, epsilon prime is here, 1 is here, of dt over f of t, and f of 0 is equal to 0. You want to evaluate such an, you have, in fact, this is equal, it is very easy to see that this is just equivalent to 1 over f prime at time 0 times minus logarithm epsilon prime f prime of 0. It is just this integral when f of 0 at 0 is 0 is equivalent to this quantity. This is the reason for this formula. And for the it will always come like that, and for that reason. At generic points, metric complexity will always be a formula of this type with this kind of invariant, and at singularity you get this logarithm with the derivative at the point of the function. It is always like that, not only for Martinet points, but in the future. Okay. Then, in fact, this is very general behavior. It means that, in fact, you spend a very, very little time to spend a very, very little height, to pass through a very, very little height. But after the asymptotics of the time when you reach the, when you are close to this limit cycle, introduces this logarithm, in fact. It is like that. Okay. How to prove this? This first formula, you just use the we just use the normal form in normal coordinates, and we see that W dot is equal to gamma over 2. This was the times y over 2 u1 times minus x over 2 u2. This is the last line of the normal form, well, gamma. So you write this gamma as a gamma 0w over 2 y over 2 u1, sorry, here, plus k some function which is of order epsilon, because it is something in x and y, linear in x and y, it must have order. Inside the tube, we know that x and y are smaller than epsilon. And you have this times y over 2 u1 minus x over 2 u2, and then you divide here, then dw over this gamma dw gamma 0w I forget about the k epsilon. You will rectify by yourself. It goes outside. It is equal to, so it is smaller or equal to y and x. So this is scalar product. There is not 2. 2 is here. So I put the 2. It remains the scalar product of xy, of minus yx, with u1, u2. But u1 square plus u2 square is equal to 1. The norm of u is equal to 1 because the geodesics are parameterized by the curves our curves we parameterize by arc length. Then this is smaller than just the norm of xy, which inside the cylinder is itself smaller than epsilon. Okay, dt. And then you integrate and you get the formula that I gave, the alpha is here. You get that, sorry. So you get that epsilon t is larger than 2 times the integral of dw over this alpha w that I consider plus something of order, epsilon t plus, okay, I forget about the term of order. Then t is larger than 2 over epsilon sum dw over alpha w, but t is the length because I am parameterized by arc length, okay? T is the length because I am parameterized by arc length. But to get the metric complexity, I have to divide by epsilon. Then the metric complexity of epsilon is larger than 2 over epsilon. This quantity, okay. Then I get that. I get this inequality. And to get the reverse inequality, you just have to compute integrate the equation of the vector field that you get on the cylinder. You do it explicitly, and you see that in fact, following the trajectories that I described, you get exactly the equality. This is a proof. It is very simple. Okay? How much time?
5 minutes left.
5 minutes? So I finished with, I completely finished with the 3-dimensional case. Notice that I did not only treat the contact case, 1 step, but also 2 steps, because at Martinet points you are 2 steps. Then I continue with current 1. Maybe I just start to describe. I just state the result. And I show the proof next time. And after k equals 1, I will go to k equals 3, where we will see appearing this convexity property that I was talking about previously. Now, k equals 1. Okay. Again, I take a one form omega, which annihilates delta, and which is 1 on gamma delta. It is unique up to multiplication by a function which is 1 over gamma, which does not affect the following. This one does not affect the following computations. Then again, I consider d omega. D omega, then this d omega for this one form along gamma. This d omega restricted to delta is a skew-symmetric matrix. So at point t, d omega at gamma of t, I call it A of t. it is bilinear. You put it into a skew-symmetric matrix by using the metric, okay? Then you get a certain matrix A of t. And by the way, again, this matrix A of t is just the matrix of the bracket modulo delta mapping at the point t of the curve gamma, and in this coordinate. And then the formula for metric complexity is like that. Metric complexity of epsilon is 1 over epsilon square, again, the integral of dw over just the L2 norm of this matrix AW, which coincides, of course, with the previous formula. And in fact, in dimension more than 3, but corank 1, we still have the tangency points, but we do not have logarithmic points anymore. It is for one step, having logarithmic points is generic only in dimension 3. Okay. Then, in fact, for k equals 1, but the dimension of the distribution, but the dimension of the space larger than 3, the formula is always this one, which I prove next time, and after I pass to the general case, k smaller or equal to 3. And after, complications will start.